Hello everyone, my name is Dongyu Liu, currently a postdoc from MIT Data to AI group. It's our great pleasure to present our work, TadGAN, time series anomaly detection using generative adversarial networks. Time series data appears in many applications, such as satellite telemetry, server metrics, and even the pandemic statistics like confirmed case numbers. So detecting and analyzing anomalies in time series becomes very important, especially for some critical use cases such as cyber intrusion, fault detection, and preventive maintenance. In our paper, our targeted research problem is, given a multivariate time series, find out a set of anomalous time segments that have unusual values or do not follow the expected temporal patterns. The image below shows the basic process starting from the raw signal data processing, use the machine learning models to produce a list of anomalous time segments, and finally ask the domain expert to analyze these time segments. To formally define our problem, let's say X is the given time series. Now, our job is to find a list of anomalous sequences. Each sequence is a continuous sequence of data points in time. We may note that, unlike traditional time series classification problem, the anomalous segments here have different time lengths. So what makes this problem so challenging? This is because we don't have any previous identified known anomalies to train and optimize the model. We also do not have any knowledge about what is normal to make anomalies stand out. Finally, we don't have clear strategies to segment signals. So, all of these challenges suggest the necessity of using an unsupervised machine learning approach to solve our problem. For a typical machine learning method, here I will introduce the basic workflow. First, given the raw time series, we will ask a machine learning model to learn patterns. So when the model learns enough knowledge from the data, we will know what should be expected for a time series. If the expected time series deviated largely from the actual ones, then that indicates there is an anomaly. So our first question now would be how the machine learning model can learn what is expected. In this work, we will introduce how we use GAN to do this. We all know that GAN is one of the most interesting and popular deep learning models. It has very good performance on image data. The idea behind the GAN is that generators learn how to construct a fake image to fool a discriminator, whose job is to identify fake examples from real ones. They compete each other to be the best at their job. So as shown in the picture below, all the faces here are faked, but they look so real. In our work, we will use the same intuitions to reconstruct time series using GANs. I will introduce the details in the next session. So with the use of GAN, we now know what is expected. And the next question we want to ask is how to calculate the discrepancy between the actual time series and the expected time series. In the following, I will introduce all of these details. Before that, I want to summarize the key contributions of our work first. At first, we propose a novel unsupervised reconstruction-based anomaly detection method using GANs. Second, we propose a novel method to calculate the discrepancies through combining reconstruction errors and critical scores. Finally, we develop an open-sourced benchmarking system for time series anomaly detection, and we also conduct an extensive evaluations using 11 time series datasets. In this session, I will introduce how to use GAN to perform time series anomaly detection. To do so, we need to first address the following three questions. How do we create the expected signal? How to calculate the discrepancies between the real and the generated signal? And how to evaluate the anomaly detection pipeline. Before diving into each of the questions, let me first introduce the full pipeline for time series anomaly detection. The pipeline involved multiple stages starting from data preprocess, model training, make prediction, compute errors, find the threshold, and finally return a list of anomalous segments. As a note, for each stage, there might be different options we can choose. For example, we have multiple machine learning approaches to help find the expected signals. We classify them into two main classes, prediction-based and reconstruction-based. Prediction-based method learns a predictive model to fit the given time series data. The anomaly score at time t is measured by the residual error between the predicted values and the true values. The basic assumption here is anomalous values should not be able to be predicted as well as the normal ones. So the higher the residual error, the higher anomaly score this data point is. Reconstruction-based method learns a model to capture the latent structures of the given time series data, and then reconstructs the data using their latent representations. See the image below. The model maps the original time segment to a low-dimensional space, and then remap it back to the original space. So the anomaly score can be defined as the reconstruction errors between the reconstructed time series and the original time series. The assumption here is anomalies lose information when they are mapped to a lower dimension space, thereby cannot be effectively reconstructed. So generative adversarial networks are reconstruction-based method, where we can aim to learn the patterns of the signals and then generate them. We train the generator G to reconstruct time series data from observed set of telemetry data. We train the discriminator D to distinguish between generated and the real-time series. As I introduced before, the core ideas behind reconstruction-based method is to learn a model that can encode a segment of time series and then decode the encoded one. In addition to the original GANS structures, TadGAN further introduced an encoder E and an additional discriminator CZ to distinguish between the encoded signals and random noise. E maps the original time series to a low-dimensional space, and G reconstructs it back to the original space. To train the two mapping functions, the final objective has two terms. The first term is Wasserstein losses. So these losses match the distributions of the generated time series sequences to the data distributions in the target domain. So generator G generates samples from random latent samples. Critic X is the function of Wasserstein-1 distance with the purpose to distinguish between generated samples and real samples. Similarly, we introduce Wasserstein loss for the mapping function E and its critic CZ. The purpose of CZ is to distinguish between random sample and the encoded samples. However, training the GAN with Wasserstein losses alone cannot guarantee mapping individual input Xi to a desired output Zi, which will be further mapped back to the Xi. So here we introduce the second term, cycle consistence loss, to the objective functions. It minimizes the error-to norm of the difference between the original and the reconstructed samples. Combining all of the terms together, we now have the final objective functions as shown here. With this, we can obtain the well-trained mapping function E and G. So now we can use E and G to reconstruct time series. Here we show an example of the reconstructed time series. The blue line here is the actual time series, and the orange one is the reconstructed one. We now have the expected signals. Then the next question would be, how can we find the discrepancies between the real and the expected signal? We call this error calculation. Basically, we have the two things that can be used here: reconstruction error and the critical score. Reconstruction error is the error computed from finding the difference between the two signals. In our paper, we presented the following three functions to compute the reconstruction errors. First is pointwise difference. It computes the difference between the true value and the reconstructed value at every time step. Area difference is an average difference between the areas beneath the two curves. This method is a good to identify the regions where small differences exist over a long period of time. Dynamic time warping computes the DTW distances. It is also able to identify the regions of small differences over a long time period of time, but it can also handle the time shift issues. The critical score can be viewed as the confidence level of how sure the model is that the signal given is real. It can be utilized to measure the error as well. We introduced two different ways to combine the critical score with the reconstruction error. The first one is a convex combination, where the alpha here controls the relative importance of the two terms. The second one, we try to multiply both scores to emphasize the high values. So once we have the error scores at each time step, we now can use the thresholding strategies to find out anomalous segments. We here employ locally adaptive thresholding method. For a given time window, we use 4 standard deviations from the mean of these windows as the current threshold. So doing like this, it is very helpful for extracting contextual anomalies. Now we obtain a set of anomalies. The next question would be how to tell if the pipeline is good. In fact, this is a question that can only be determined when I have some known anomalies. Such dataset is not expected to be present in some practical domains. However, there are some existing datasets that contain this piece of information in our benchmark. The idea behind our evaluation approach is that in a typical anomaly detection setting, there are domain experts that monitor the signals. If the model drew attention to the location of the anomaly, it should be rewarded. Therefore, we record the rewards as follows. If a ground truth segment overlaps with the detected segment, we count 1 true positive. If the ground truth segment does not overlap any detected segment, we count 1 false negative. If a detected segment does not overlap any labeled region, we count 1 false positive. In this session, we will report our evaluation results to demonstrate the effectiveness of TadGAN. To evaluate the algorithm, first, we need to have some datasets with known anomalies. We collected 11 datasets from 3 reputable data sources like NASA, Yahoo, and NAB. The table below describes the characteristics of each dataset. For example, Yahoo A1 dataset contains 67 different signals. 178 anomalous time segments, among which 68 are point anomalies and 110 are collective anomalies. We also count the number of anomaly points and the number of points whose values are out of the normal distribution. So the percentage of out of normal distribution points can somehow reflect the degree of difficulty of this dataset. We compare our algorithm with the following algorithms including LSTM, ARIMA, DeepAR, LSTM autoencoder, HTM, TadGAN, and MS Azures. So the letter P here indicates that this is a prediction method, R indicates reconstruction-based method, and C indicates commercial solution. The table below shows the benchmarking results. The methods are ranked based on the average F1 score across all the datasets. It is very clear for us that to observe, TadGAN outperforms all the baseline methods by having the highest average F1 score, which is 0.7. One interesting question we may ask is how AI machine learning models made progress over the last decades. So to answer this, we compare all the baseline methods with ARIMA, the popular statistical model first proposed in 1970 for time series forecasting. So the chart on the right shows how much improvement in F1 score is gained by each model compared with the ARIMA. TadGAN achieved the best overall improvements with an over 15% improvement in score, followed by LSTM. Unfortunately, all the remaining models seem struggle to beat ARIMA. Another interesting question would be how well do autoencoder perform compared with GAN-based method. Here we highlight the 4 reconstruction-based methods including TadGAN, LSTM autoencoder, dense autoencoder, and TadGAN. On average, TadGAN is doing the best, followed by LSTM AE, dense AE, and then TadGAN. One interesting finding here is that LSTM AE and dense AE perform badly on Yahoo A3 and A4 datasets. These two datasets contain a large number of point anomalies, so we suspect that autoencoder might easily get overfitted, while adversarial learning does not have this type of issue. We have more insight regarding this table reported in the paper, so if you have more interest, please refer to the paper for details. In addition to the benchmarking results, we also conducted an ablation study to investigate how valuations of variable calculation impact the results. So from the table, I want to highlight 3 insights here we thought interesting. First, critic alone is unstable, but it improves the result when combined with the reconstruction error. Second, dynamic time warping is better than other 2 reconstruction error types. And lastly, multiplications is better option than convex combination when we are trying to use the combinations of critic score and the reconstruction errors. Finally, let's have a recap of our contribution. First, we propose a novel unsupervised reconstruction-based anomaly detection method using GAN. Second, we propose a novel method to calculate the discrepancies through combining reconstruction errors and critic scores. Third, we have an open-source benchmarking system for time series anomaly detection and extensive evaluations using 11 time series datasets. You can follow the GitHub links here to find our benchmarking code. That's the end of my talk. Thank you.